Okay, in this lecture, we're going to talk about the Lebesgue measure. I realized earlier on that I missed the uniform distribution or uniform probability measure when you have a finite set. So I'll introduce that first because it sort of leads to the Lebesgue measure naturally. So if you've got a finite set as your sample space, then there's a natural measure which we're going to denote U omega on omega with its power set. And this measure is the uniform measure. And, well, you can probably guess what it does from the name if you haven't seen it before. It assigns to a set the size of the set divided by the size of omega. In terms of densities or probability mass functions, which I introduced previously, this is associated to the mass function, which is 1 on omega for every point omega, for all omega in big omega. Okay, and yeah, the idea is that this is uniform because it only depends on the size of A, the number of elements in A. If you want to think of it as quite a bit more abstractly, there's an action of the symmetric group on omega, symmetric group of order the size of omega, and this is a measure which is invariant under the symmetric group, and that's why we say it's uniform. So leading from that, we're going to come up with another measure which is known as the Lebesgue measure, and this is invariant under translations, and it's a measure on RD with its Lebesgue measure. Okay, and we're not going to really go over the whole construction, but I'll explain it. So, and this is also going to give us a way to get away from things such as the Banach-Tarski paradox. It is the Lebesgue measure which the Banach-Tarski paradox sort of messes with, in that the sets that you get from the Banach-Tarski paradox are not Lebesgue measurable. In other words, you can't make sense of their probability or their volume with respect to Lebesgue measure. Okay, and how does one do this? So we're going to, Lebesgue measure. Yeah, so this is, I believe it's a French name. That's why you don't pronounce most of the letters. Yeah, it's like Lebesgue. You don't really say the rest. I think when I learnt this stuff, I first read it on my own and I had no idea how to pronounce this word, and I was quite confused when it actually came up in lectures for a little bit. Yep, so what do we do with this? Well, we'll just do it on R first with the one-dimensional Borel sigma algebra. Well, this is really the intuitive notion of volume or length that you would expect, except completed. Well, completed is a technical term, except extended to a measure on every set in here instead of just the really, really nice, obvious ones that you know how to measure with a ruler. Although it's not far off measuring things with a ruler. Okay, well, what do? You define it. You start with, I guess, pre-measure, so lambda dash, which takes an interval AB and sends this to B minus A. You don't really need to worry about open or closedness on either end. And, well, you show that you consider the well, let's call it a collection. You consider the collection of sets formed by finite unions and complements of such intervals. Okay, so this set we're going to call G. So, i.e. the smallest set which contains all these closed intervals and is closed under finite unions and complements. Well, you can make sense of what lambda dash does there by just things in here are going to be pretty close to, well, yeah, they're going to be unions of closed or open intervals. You know how to assign the length to those by just sort of, or if you've got this interval, its length is going to be the sum of these lengths. And because we're only dealing with finite unions, things aren't going to get too crazy. And then upon extending, so lambda dash extends to G, and then we can apply the Carathéodory extension theorem. A slight extension to what I showed you previously, that was for sort of probability. Well, yeah, that was for probability measures. This Lebesgue measure isn't, so it doesn't have total mass 1 because sort of R goes on forever, whereas these intervals, if you want to give them a measure like this, that's already, if you look at the interval 0 to 2, that's too big. So this is a not finite measure, say. And then a version of Carathéodory extension theorem well, it gives you an extension which we denote lambda, which goes from all of the Borel sigma algebra to, well, we actually need to include infinity too, for the same reason that this is, the length of R is infinite. So you actually need to include infinity here. And yeah, so this provides the analog of the uniform measure when you are working on subsets of R, in that it's translation invariant. So first of all, if you translate an interval like this, that doesn't change this notion of length. You can show that therefore it's not going to change the notion of length or volume or measure of any of these sets in G, and therefore it's not going to change any of the lengths. Like translating doesn't change the length of things in the Borel sigma algebra. Okay. So we'll also often want to restrict this lambda, and that is then actually going to be able to give us a probability measure when we normalize it. So we also obtain lambda, well, let's say for A in B1, we can consider lambda restricted to A, which goes from the Borel sigma algebra restricted to A. See the addendum from the second lecture where I explain what this subscript A, how you restrict. So this is going to go from 0 to lambda of A. And well, here it's really just lambda restricted to A of some set, let's call it B, is really just lambda of B for B subset of A and Borel measurable. Okay. So this is still a little bit away from the uniform distribution because the probability of the full set isn't 1. So how you fix that is you just divide by the measure of the full set. So the uniform distribution on A is, well, applied to a set B is really just lambda of B divided by lambda of A for B in the Borel sigma algebra of R restricted to A. Okay, and this should really agree with your intuition about what volume is. There's just this caveat that we've got to extend to a sigma algebra, and that means we have to use some heavy machinery like Carathéodory's extension theorem. Yep, and now we'll talk about it in higher dimensions. It's going to go exactly as you would expect. So in higher dimensions, well, now we're going to be talking about higher dimensional measures. So we're going to instead start by having a pre-measure defined on sort of boxes. Well, let's just A1, B1 times ... times AN, BN. And this is exactly what you should expect. It's the product A1 minus B1 times AN minus BN. And then you do the same procedure. You show that this has an extension to the set of sets which can be obtained by finite unions or complements of things like this. And then you use Carathéodory extension theorem, and this gives you Lebesgue measure, which occasionally you'll see it with an n, signifying that we're in dimension n. But as with the Borel sigma algebra, where I've said we're sometimes just going to leave that off, you also often leave off the n for the Lebesgue measure. And exactly as we had up here, you can normalize this when you're on a set of finite measure A. And we'll define that to be the uniform measure. So for A in B, N, I suppose, with lambda A less than infinity and greater than 0, really. We define uniform measure on A, and this is going to go from the Borel sigma algebra restricted to A to 0, 1, and it's going to do what you would expect. It's U of A of a set B is equal to lambda n of B divided by lambda n of A. Okay, so, and again, this is going to be translation independent because translation of these boxes preserves their measure, preserves this measure. Okay, so now I need to talk a little bit about Lebesgue integration. We're really not covering this in any depth, but it's important to note that we're going to talk about integration on spaces other than R, and it's going to be with integration other than the Riemann integration that you may be familiar with. Although it agrees with Riemann integral, and you're not actually going to need to compute anything that you can't compute with the Riemann integral anyway. Okay, I'll just introduce this here. Lebesgue integral. Okay, well, for the Lebesgue integral, we're not going to go over the definition, but for a function f which goes from Rn to R, say, we say f is measurable, technically Borel measurable, if, well, there are a few different options, but the one we'll stick with is that f inverse of any set minus infinity to c is in the Borel, is a Borel set for all c in R. Okay, and having these pre-images, so this is sort of like a pre-level set. You look at all the points at which f is less than or equal to c. Having these measurable, and you know how to assign volumes to sets in here, this allows you to construct a much more refined integral than the Riemann integral, known as the Lebesgue integral. There are many reasons why sort of mathematics has moved away from the Riemann integral. This Lebesgue integral is a lot easier to prove well, the definition is a lot more refined in that you can prove things for it a lot more easily. It has it has a wider range of functions you can integrate. There's a natural way to replace this Rn, and like you could possibly guess that this is going to work for whatever measure space or probability space you put here instead. And then you would swap this for the relevant sigma algebra. Yeah, so overall it's better, but the key, which is going to let you mainly ignore this, is that Lebesgue integral is exactly the same as Riemann when the Riemann integral exists. Okay, but there are natural functions which are definitely not Riemann integral, but are very, very easily Lebesgue integrable. Okay, and the point from here is that, well, we can come up, well, this condition we're going to see again when we get to random variables. So it's an important condition. It's nice to see it a little bit early. Another thing is that we can use this to define a density for measures or for probability measures on R, which mimics the probability mass function we introduced on countable sets. Okay, so we suppose we have a function, so rho from R n to 0 to infinity. Note, I'm including infinity here again. You don't need to worry about that. You can cut it out instead if you would prefer, but we don't really need to. Such that, well, we want it to be measurable. So rho inverse of minus infinity to c is in the Borel sigma algebra for all c in, well, 0 to infinity. And such that the integral of rho of x d lambda of x, so this is integration with respect to Lebesgue measure. Just think of this as, yeah, I'm not even going to write that. Just think of this as integration with respect to x, such that the integral on the whole space is equal to 1. Then you get a probability measure out of this. Then P of A defined to be the integral over A of rho of x dx. Well, for A in the Borel sigma algebra is a probability measure. And we say that in this case, we call rho a density or probability density function. Yeah, probability density function for P. Okay, and this is very analogous to what you get in when you replace RD with the countable set. Now, one thing that's different is that not every probability measure on RD, which is a probability measure on the Borel sigma algebra, they don't all have densities. So note that delta omega does not have a density. For omega in RD, where this is the Dirac measure that I've introduced previously. Okay, regardless, well, sort of what physics does is pretend that this measure does have a density, and that's what they call the delta function or Dirac delta function. It really doesn't, but you don't need it to. You can just use it as a measure. Okay, and I believe that's it for this lecture. Yep, so yeah, we will see the Lebesgue integral again later on. I just thought I would introduce it now since we've talked about Lebesgue measure. You really can just treat it as a Riemann integral if you haven't seen the Lebesgue measure, or sorry, if you haven't seen the Lebesgue integral before. Okay, see you next time.